Hello everyone, myself Dr. Chinna Dastagiri Goud, Assistant Professor from EEE Department. So today we are going to discuss about the topic Principle and Operation of DC Motor. So before going to the Principle and Operation of DC Motor, so we have to know some little bit basics about what is the motor action, how we will find out the motor direction, all these things. Previously we seen the construction of a DC machine. Either a generator or a motor, it has the same construction. We discussed about it and we seen the operation of DC generator and what is the principle of DC generator. So today we are going to see about the principle of motor action. Before going into the topic, so we will see some basics. So as we know that what is the motor means, converts electrical energy into mechanical energy. Electrical energy into mechanical energy. Right? So this is the motor. We seen already we discussed about this. So what is here mechanical energy? Especially in motor action, we know that it is a rotational motion. So whatever is the mechanical energy means, it will try to force the conductors to rotate. So we will provide the electrical energy to the machine, then it will start rotating. Like we will see the examples of fan. So we are providing the electricity, it will start rotating. So this is the main motor action. So what we are saying that when we are providing electricity, it will start moving. So it will basically the motor action is happen by the Lorenz Force Law. So it will utilize the Lorenz Force Law. So this is the principle of motor action. So what Lorenz Force Law is saying that, so when a current carrying conductor placed in a magnetic field, it experiences a force. It experiences a force. And the amount of force F is equal to BIL sin theta. The amount of force it is experienced in that magnetic field is BIL sin theta. What is this BIL sin theta? Where B is equal to magnetic flux density, and I is the current through the conductor. I is current through conductor. And L is the length of the conductor, because our complete active sites only will happen. We see in the generator action only active sites will participation in the energy conversion. So this is the length of the conductor. And then what is this theta? The angle between the conductor and the magnetic field density. So angle between conductor and B with magnetic field density. So the Lorenz Force Law is saying that how much force it is generating and how it is generating. But we have to know what is the direction of that conductor is moving. So either it is, if you take the circular motion, it is rotating in clockwise or anti-clockwise. If you take the linear motion, it is going forward or backward. So this will be known by the Fleming's left hand rule. As we know that for generator action we see the Fleming's right hand rule. So for the motor action we will see the Fleming's right hand rule. So we will see that one also here, a little bit we will discuss. That is, so to know about the direction of the conductor, we will use the left hand rule. Right. So what is the Fleming's left hand rule? So Fleming's told in right hand rule, he utilized the three fingers which are the perpendicular to each other, and he find out the direction of the current. So here similarly he will use the three fingers of the left hand, and he will find out the what is the direction of the conductor move, how it is moving. Okay. So same thing he will utilize. We have three things. So I told you the basic principle in the machines is electromagnetic conversion. So here also electromagnetic conversion. So either if you keep your side, this is electromagnetic conversion. So the middle finger will represent the electrical, that means the direction of the current, in which direction we are sending the current in the conductor, and the forefinger will represent the field, flux or field. So whatever which direction it is going, the field flux it will show. If you keep these two fingers in the direction of those things with perpendicular to each other, then we will find out the direction of conductor movement. So he said that we have to take the three fingers of the left hand and we have to keep 90 degrees with each other. So this forefinger is 90 degrees with the middle finger, 90 degrees with the thumb finger, 90 degrees with the thumb finger. Similarly, thumb finger is 90 degrees with the forefinger and 90 degrees with the middle finger. As I said in the generator action also, you take the corner of a room. So if when left hand rule you are taking, you just create that one corner. So left hand corner if you take, so this line is representing the current and this line is representing the flux, and thumb finger is representing the movement of the conductor. So right hand means right hand, if you take the right hand corner, then you will get it the clarity. So right hand corner you will take, right hand thumb rule you can understand, and left hand you will take, so left hand left side corner you can take. So Fleming's left hand rule, so as I am just mentioning, so what are the fingers we have? We are using the thumb finger. So first I am writing in reverse manner because we are taking the middle finger and forefinger. These two are in direction you will keep, you will get the thumb finger. So in the middle finger, so middle finger will represent the current. So that's why I am giving as a double quoted MI. So this is the middle finger. So represent the current direction. Represent the current direction in the conductor. And then forefinger, field flux. Forefinger will show the field flux. Field flux direction. Field flux direction. If you keep these two fingers in that direction, then we will get the finally the thumb finger motion of the conductor. Motion or motion of the conductor. So if you keep two fingers in one direction, the third one will show the motion conductor. So these two fingers will keep. So these are the basics, little bit we have to know before going to the principle of motor action. Now we will take one example and we will explain the principle of motor action. So let us consider, a magnetic field. Let's consider a magnetic field with two number of poles, that is north pole and south pole. So we know that two number of poles. So the flux will flow from north pole to south pole, N pole to south pole, S pole. So we know that. So now I'm going to draw a field which I am taking to understand the concept. So suppose this is my North Pole and then this is my South Pole, and we know that flux will flow from the north to south. Flux will flow from the north to south. Right? Which has a flux density of B. It has the flux density B flux density. Okay. Now what we have to do according to Lorenz Force Law, we have to take a conductor. We have to take a conductor. Consider a conductor. Consider a conductor with length L, carrying current into the conductor, So what is the meaning of into the conductor? So it is flowing. So already previously we discussed that. Suppose I am considering a conductor. So let us take, I have a conductor. If I will keep in a 2D plane, so it will come like this. So this is my conductor. So if suppose this pen is my conductor, if I will keep towards me, pinpoint I have kept it towards me. So if it is coming current inwards, so that means it is moving from this point to pinpoint. It is coming outward means from pinpoint to outwards. That means towards you, towards me. If it is coming towards me, it is into the conductor. It is coming towards you, it is out to the conductor. So into the conductor will represent with the into mark, cross or X. So this is into the conductor. And we know from right hand thumb rule, what we know from right hand thumb rule, suppose this is a conductor, it is carrying a current, it will generate a flux. And right hand thumb rule will give the flux direction. If you keep your thumb finger in the direction of the current, remaining fingers will show the flux direction. Here if you observe, current is going inwards. So if I will keep current is going inwards, you see the flux lines, the remaining fingers will be in the clockwise. That means the conductor will generate the clockwise flux lines. Right? So these are the flux lines generated by the conductor. So from where we taken this one, this is, so from right hand thumb rule, the direction of flux in the conductor is clockwise. Right? So now we want to check the Lorenz Force Law. We want to know the principle of motor action. So what we have to do, this current carrying conductor we have to keep in the magnetic field. So now we have a magnetic field. So this is my magnetic field. So this is north and this will be the south. So what I am doing, I am keeping my conductor. I am going to keep my conductor. So this is my conductor. So I am taking little bit big to understand the concept. So I am taking my conductor. Okay. So this conductor is inwards. So what will happen? Flux will be in the clockwise direction. What about the magnetic flux? It is always from north to south. It is always from north to south. Here what will happen if you observe in the conductor, so if you see this is conductor for us, suppose we will take this side. So on the left side, so I am considering this is my right side. So on the right side, if you see the flux is from north to south and the conductor flux also in the from top to bottom. So it will add to the flux of the magnet. So this side flux density will increase. So this allowed to add the flux density. It will become more flux density. As we know that flux density means flux per unit area. Now flux lines are increasing. It is adding the flux. Coming to on the left hand side, if you see the flux is opposing the magnetic flux. It is opposing the magnetic flux. So what will happen? So this side it will weaken the flux. This side it will weaken the flux because it is opposing. So what will happen on the right side? We have the maximum flux and left side we have the less flux. So what will happen? Automatically the flux difference will allow the conductor to move towards this direction. It will apply some force. So this is the Lorenz is saying, when you will keep the current carrying conductor in a magnetic field, if you keep the current carrying conductor in a magnetic field, it will experience a force. It will experience a force. And from Lorenz Force Law, we know that this F is equal to BIL. F is BIL. Suppose it is doing some angle theta, then it is BIL sin theta. This is the force experienced by the conductor. So here we can check, already we seen the direction of the flux because of the direction of the conductor because of the flux. But if you use the Fleming's left hand rule, it has to apply same. So you see from north to south, so from top to bottom, so it has to move to the direction. So this is the direction from north to south. This is the flux direction. So I have to keep my forefinger because it is the feed flux from north to south, and current is inverse. So current is inverse, field is north to south. My thumb finger will be from my right to left. So similarly, same we can apply for all the conductors in the motors. Whenever the conductor is experiencing the force and which direction it will move, we can say by using the Fleming's left hand rule. So here this is the principle of motor action. So I will write the conclusions also. So what happened? So when the conductor, the current carrying conductor, we have to say the current carrying conductor kept in a magnetic field, so what happened? On the right side of the conductor, the flux supports field flux, and on the left side oppose the flux, field flux. Moves from right to left, So just I am asking, suppose I want to move the conductor from left to right, what we can do? From left to right, if you want change, we can do the two things. If we change the positions of north and south, then what will happen? Flux will be upwards, current is inwards, my thumb finger will be from left to right. That is one option. And another option is you take the current outwards. So north to south it is downside only, but I am taking current is outwards. Current is outwards. So then also the direction will change. Then also current will change. Because current is towards me, it is north to south. So my thumb is towards from left to right. Okay. So just you will check it by your own. So this is the principle of motor action. Okay. We taken a current carrying conductor, we kept in a magnetic field, and what is the force it is experiencing. So next we are going to check what is the operation of DC motor. So up to now just what we done, so we considered that what is the principle of motor action. When a current carrying conductor, when we kept in a magnetic field, it will experience as a force. Okay. So now we are going to check what is happening in a DC motor. What is the operation of DC motor? So here what I am doing, I am considering a 4-pole machine. I am considering a 4-pole machine. So 4-pole machine, so 2 north pole, 2 south pole. So I am drawing here. So I will take a 4-pole machine. Considering 4-pole machine, suppose this is north pole, then it is south, then it is north, then it is south. So in a 4-pole machine, I am you keeping my armature. So I want to keep my armature. So let us make this is my armature. I will consider some conductors also. I will consider some conductors. Let's take 12 conductors and 3 conductors for each pole. So this is 1, 2, 3, okay, 4, 5, 6. Intentionally the conductors on the north pole I am drawing with one color, and under south pole I am drawing with one color to understand, to differentiate the conductors. So actually it will rotate, it will change, all the conductors will go through the north and south, but this particular instant I want to take, right. So each pole we are giving the 3 conductors, so total 12 number of conductors. And we will also consider that, whatever the conductors on the north pole taking the current inwards, and whatever the conductors under south pole, they are taking the current outwards. Okay, their current is outward. So outward current we are giving with the dot, inward current we are giving with the into. This notation already we see. Okay. So we'll write it. So what I am saying, just we'll go through this. Let us consider a 4-pole machine, 4-pole DC motor, 4-pole DC motor with 12 number of conductors, Okay. The conductors under north pole, taking current inwards, and under south pole, conductors current direction is outwards. It's not compulsory that under north pole it has to be into the conductor, and under south pole it has to be out to the conductor. So if you provide, the direction will change. That also we'll discuss. So now we consider a system or motor. So in that one we have 4 poles and we have 12 conductors, and we know that a flux will flow from the north to south. So I am giving the flux direction. So from north, flux will come towards the armature, and in south it will go towards the pole from the armature, right? So this is the flux, whatever it is coming. So now we have to understand what is the operation of this motor. So now we provided the current. So we know that it is experiencing a force from Lorenz Force Law. So as current carrying conductor kept in a magnetic field, it will experience a force. This is from which law? Lorenz Force Law. Right? So what is the direction of the current? So from Fleming's left hand rule, so what Fleming's left hand rule is saying, what is the direction of the current? So here what I will do, I will consider the test cases. Suppose consider this is the conductor 1 under north pole, conductor 2 under south pole, conductor 3 under north pole, conductor 4 under south pole. Or otherwise we will give the numbers. This is 1, 2. We will do one thing, we will give the numbers to the all conductors. Okay, so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So total 12 conductors are there. In this one, I am considering the conductor 1. So Fleming's left hand rule will take some example. Consider conductor 1, 4, 7, 10. So these 4 conductors will be. So if you consider the conductor 1, so conductor 1, it is current is into the conductor, the direction of the current is into the conductor, and flux is from north it is coming. So we have to find out the direction. So what we will use? We will use the Fleming's left hand rule. So Fleming's left hand rule, what it is saying? We have to keep the middle finger towards the direction of current. So we will keep into the conductor. That means into the conductor. And then the flux direction is from north to south. It is from up to down. So from up to down. If you see my thumb, it will be from my right to left. So the direction. So first direction, the direction is from left to right. So the direction of the conductor 1 is from left to right. So this is the direction of conductor 1. This is the direction of conductor 1. Next we will see the fourth conductor. So here if you see fourth conductor is under south pole, the current direction is outwards. So my middle finger is outwards, and the flux also towards the south pole. So the conductor is moving upwards. That means the fourth conductor is moving upwards. Next we will come to the seventh conductor. So seventh conductor, current is inwards and flux is upwards. Okay, the direction is from left to right. So the seventh conductor is moving from left to right. And then left is 10th conductor. So the 10th conductor, if you observe 10th conductor, current is outwards and flux is towards the south pole. So we have to keep, this will be outside and this will be the flux will be this direction. So the direction is from top to bottom. So the 10th conductor. So 10th conductor is from top to downwards. So if you observe clearly here, the 4 conductors, if you observe the direction of the 4 conductors, here you see 4th conductor is moving upwards, 1st conductor is moving from right to left, 10th conductor is moving from downwards, and 7th conductor from left to right. So they all are rotating in a anti-clockwise direction. These all are rotating in anti-clockwise direction. If you want to check it randomly in any conductor, all the conductors will follow this one only. That means each conductor is experiencing the force. Each conductor is experiencing the force. All the forces combinedly will move the armature in anti-clockwise direction, and they develop a combined torque. They will develop a combined torque. That is the torque of the DC motor. That is a combined torque. I hope you are clear. So we consider the 4 conductors. From the Fleming's left hand rule, consider the 4 conductors. We can understand all the conductors moving in anti-clockwise direction. Anti-clockwise direction. Or counterclockwise also they will say. So anti-clockwise direction. So this is the operation of DC motor. This is the operation of DC motor. Suppose if you want to change the direction, you want to move all the armature or all the conductors in clockwise direction, what you can do? So simply we can change the direction of flux. How we can change the direction of flux? We know that the north pole is generated by using the field windings. So field winding currents, if you are able to change, field winding currents are if you are able to change. So north pole will become the south pole, south pole will become the north pole. That is the one thing. Or otherwise another thing is, if you change the plug direction, that means current under north pole if you give the outward direction, and under south pole you will give the inward direction, then also direction of the current will flow. So there is 2 methods. Either we can change the field current or we can change the armature current we are providing. Because we are giving the electricity, it is generating the mechanical energy. If you change these 2, the direction of the motor will change. So this will come to the operation of DC motor. But in the operation of DC motor, one more important point is there, that is the EMF. Sir, why in generator EMF will come? Because we know that the Faraday's law, according to Faraday's law, when a conductor cuts the flux, it will generate the EMF. Yes or no? Here you see, we provided the current, but after that what happened? This conductor starts moving. The conductor starts moving. So when conductor starts moving, it is also cutting the flux. It is cutting the flux, because if suppose the conductor 1, if you consider, when it is moving in anti-clockwise direction, first it is under north pole, then it is under south pole, it is cutting the flux generated by them. So that means it is generating an EMF. It is generating an EMF. When it is generating an EMF, what is the direction of EMF? How we will find the direction of EMF? We will find the direction of EMF by using the Fleming's right hand rule. Okay, we will apply the Fleming's right hand rule. So we will forget about the direction of the current in 1. First we will check the what is the direction of the current from Fleming's right hand rule. So if I am considering the conductor 1, north pole to south pole, from top to down, the current flux is coming, and thumb finger will show the motion of the conductor. So definitely the conductor is moving from right to left. If you see that my middle finger is towards me, that means current is coming outside. But we given the current inward. That means we given the EMF to flow the current towards the conductor, but what is happening? It is giving outwards to the conductor. That's why the generated EMF is known as back EMF. The generated EMF is known as back EMF. Simply we can say like this also. We know that the sub law of the Faraday's laws, which is which law? Lenz law. What Lenz law is saying? Lenz law is saying that the EMF induced in a conductor, will always oppose the cause behind it. Here, why EMF induced? Because of the conductor cuts the flux. Why conductor cuts the flux? because it generated a force. How force is generated? Because we are providing the current to the conductor, magnetic field is available. So from where we are providing the current? Because we are giving the EMF outside electrical energy. So it has to oppose that EMF, whatever we given the supply voltage. That's why it is known as back EMF. That's why it is known as back EMF. Just we will see that one. That is the important topic in the DC motors. What is the back EMF? So if you ask me the definition, in DC motor, when conductors start rotating, or armature start rotating, we'll say that when armature starts rotating, the conductors cuts the flux. From Faraday's laws, when conductor cuts the flux, it will induce the EMF. Hence, the conductors in motor induce the EMF, and this EMF opposite to the supply voltage. Therefore, it is known as back EMF. It is known as back EMF. Okay, this is known as back EMF. So now you understand what is the back EMF. Here you tell me, so it is inducing the EMF. So we have to find out how much EMF is induced. So that will be d phi by dt. So if you see from this diagram, whatever we see in the operation, so here number of poles is same and it is rotating with some speed. So we suppose the speed is n, we will consider it. It is rotating with the speed n. So number of poles is p and the flux is phi, and the anyhow winding will be the same like wave winding and lap winding. We see the construction is same. So A is the number of parallel paths and Z is the number of conductors. Then if any change will be there in the EMF equation? No. So it will generate same EMF equation whatever we discussed in the previous classes. So the EMF induced in the DC generator, what is the formula we see? So we seen that the induced EMF E is equal to P phi n Z by 60 A. But only the thing here will represent, this is back EMF EB. So it represent with EB. There sometimes we will represent with EZ because EMF induced in the generator. This is the EB, EMF induced in the motor back EMF, that's why EB. So here we know that already. Just again I am simply mentioning P is equal to number of poles P is equal to number of poles, phi flux per pole, phi is flux per pole, and N is the speed of the conductor, N is the speed in RPM, so armature speed this is, and A is equal to number of parallel paths, number of parallel paths, and Z is equal to number of conductors. Z is equal to number of conductors. Clear? So this back EMF, how the main significance is, it will allow the machine, that means motor, to take enough current to run the load. Enough current to run the load. Suppose this back EMF is not there, it will take the maximum current and it will generate the EMF. This EMF is opposing that voltage. That's why definitely the current value, how much current value it is taking, that will reduce. So the main significance of this back EMF is it will make self-regulated. It will make machine to self-regulate, and it will allow only the small amount of current to run the load. How much amount of current is required for the load, that much of current only it will take. So this is about the principle and operation of DC motor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.